Okay, so in last week's lab, you guys had to take some water. You could choose any amount of water at any temperature and try to raise its temperature by 2 degrees by doing something to it. So we're going to work with those concepts there. So you had a certain amount of water. We're going to look at some examples of how you guys did that. So you have a certain amount of water that's sitting in the cup. And what we're trying to figure out is, so what you guys were trying to bring out about is a temperature change. So we're going to use some terminology for this. The way we represent temperature change with a symbol is with this little triangle and then a T. So whenever you see this triangle, it means change. And we represent temperature with a big T. So change in temperature is literally this little triangle temperature. Now, some other terminology we need to know is the way that you figure out a temperature change is by figuring out how things are different at the end of what you did versus the beginning. So just like if you were tracking your weight loss, right? And you lost, your goal was to lose 20 pounds. And so you've been tracking your weight and you started out at, your start weight was 210 pounds, okay? And you're trying to lose weight, so you've been tracking it over time. And then after a month, then you find out, you weigh yourself, and you're like, oh, now I am 200 pounds. Okay, so the way we would define those is we would say this would be your initial condition, and this would be your final condition. So the way you find out the difference between them, so in this case we would do change in weight is going to be, we're going to abbreviate your weight with a W, and we're going to say, okay, what we're interested in is your final weight minus your initial weight, because we're interested in how did you change over that time. So if we do that, if we, kind of plug those in there, let me make some space here. So we'll clear out the temperature change stuff just for now, and we'll work on this weight problem. It's kind of messy. This is kind of cool, actually. All right, so we'll go back to this. So if we do this change in weight thing, we're going to say, okay, the change in weight is equal to, all right, so my final weight was 200 pounds, and we're going to subtract the initial weight. So my initial weight was 210 pounds. So when you do that math, if you take 200 minus 210, you actually get minus 10 pounds, which seems a little weird because it's like, well, why is it a negative? But we consistently do this where we say, the final minus the initial, because in this case, when you think about it, well, what happened to you? You started out at 210 pounds and you lost 10 pounds. So the way we say lost is with that negative sign. So we always set it up this way. We do the final minus the initial whenever we're looking for a change in something, because we're trying to say, okay, how is the ending situation different from the beginning situation, right? So what we're trying to do, okay, so we're trying to find, your goal was a temperature change of 2 degrees Celsius, all right? So the way that's going to work is you want the final temperature of your water minus the initial temperature of your water to equal 2 degrees Celsius. So you can go about that a lot of ways, right? So you could have your final temperature was 87 degrees Celsius. In that case, if your initial temperature was 85 degrees Celsius, then what you're going to get is, let's see, 87 minus 85. Yeah, that's going to be 2 degrees Celsius. And you'll notice that our 2 degrees Celsius is a positive 2 degrees Celsius because you guys were trying to increase the temperature by 2 degrees. If you'd been trying to decrease the temperature by 2 degrees, then we would be looking for a minus 2 degrees Celsius temperature change. So this is the first terminology we need to have. So clear slide, erase all strokes. Okay, so our target is a change in temp of 2 degrees Celsius. Now, the way that we're going to accomplish that, so the last video we looked at what happens to molecules when the temperature is going up. We're watching those molecules get faster and faster. So in order to make molecules go faster, you guys have learned about inertia. You know that molecules are just going to keep doing what they're already doing unless you mess with them. So the way we're trying to mess with these molecules is to get them moving. And the way you get something moving, if it's just kind of cruising along at a pretty consistent speed, is you need to push it, right? So we have to supply some kind of push to these molecules to get them going faster. So what we're going to represent there, the push that we're going to give, you will see this terminology. You will see the letter Q. That is the same as lowercase q. You can do it either way. And you will see these defined as heat or energy. And you can use it either way. It probably makes more sense for us to refer to energy. Okay, so Q, and I usually use a capital Q because it just looks cooler. And then energy. So we're going to think that way. All right, so we're going to take our water. So here's your water in your styrofoam cup. And let's say, so a lot of you guys started out at 18 degrees Celsius, right? So what you have to figure out some way of doing is you have to get some Q in there. You have to provide some energy in order to get these molecules moving, right? So if a molecule's, they're all kind of sitting around here, and you need to push them to get them going faster. So come on, guys, let's go. Start moving around. So you have to provide a source of energy, a Q. And you have to provide just the right amount of energy to get them to start moving faster, but not too fast, right? Because you wanted to increase the temperature by exactly 2 degrees Celsius, no more, no less. So you have to provide just the right amount of Q. So we're trying to provide some heat energy. We're going to use Q to represent that. Oops, 18 degrees Celsius. All right, so we know our target change in temperature is 2 degrees C. We know that the way we're going to accomplish that change in temperature is we're going to provide heat. We're going to provide energy. We're going to provide Q. So you guys did that a lot of different ways. I'm going to erase this picture for a moment. So let's see. There's one example. Let's see here. We had a group that was like, okay, let's take 100 mils of water, and we're going to have it be at 18 degrees Celsius. And we're going to combine it with another 100 mils of water at 22 degrees Celsius. And what happened in that case is you get a much bigger bucket of water, right? So our final, we end up with 200 milliliters of these two mixed together, right? Excuse me. And it turned out that that worked pretty well. So we were pretty close to 20 degrees Celsius. So what we ended up seeing there is we started at 18 degrees Celsius was our starting temperature. We poured in 100 milliliters of 22 degrees Celsius water, and then it settled in the middle at 20 degrees Celsius. So one critical thing to realize here that you guys all kind of saw it repeating over and over again is you have two things that are starting at different temperatures. But if you mix them together, you're going to get, they're both going to settle at the same combined temperature, right? Which you actually probably have a pretty good instinct for. You know that if you take coffee that's kind of gotten cold and you add hot coffee to it, they're going to blend together and you're going to get coffee that's kind of a middle temperature, right? You're not going to end up with a layer of cold coffee and then a layer of hot coffee and they're not going to mix. They're going to mix and blend, and then we're going to see that their temperature is going to be, they're going to reach the same final temperature. So this is going to be our final temp. And one of the critical things that you guys kind of maybe didn't articulate but all seemed to notice is that whenever you put two substances together, so in this case, we're pouring these two waters together, but some of you guys took some water and you put one of those metal cylinders in it that had the little hook on it. So you put two things together that started at different temperatures, but they're going to settle at the same temperature, at the same final temperature. So that means when you start to do calculations on all these things, and there's going to be a temptation to just go right to a formula and just start dumping things into it. If you can get these concepts first, then that formula is going to serve you much better, which is why we have not talked about the formula yet. We've just been talking about the concepts. So when you combine the metal, in this case, so maybe the metal started at 50 degrees Celsius and the water started at, say, 20 degrees Celsius, whatever their temperature is, and we may not have a reason to predict, like, well, I don't know, what's their temperature going to settle at? They're going to both sit in there for a while. We're going to put a thermometer in there and see what happens. What we know for sure is that if the water's starting out fairly cool, room temperature, and the metal's going in pretty hot, we know that the metal is going to cool down and the water is going to warm up and they're going to come to the same final temperature. So whenever you put two things in contact with each other, ultimately you give them a little time, they're going to come to that same final temperature. So we're going to look a little bit at why that is and what seems to influence it. I just do a big erase. Big erase. All right, so when you look at the data from that lab that you guys did last week, and this is something that you'll want to include in that lab report, hopefully, if you haven't already, I would say add it in. You're trying to look at what are the factors that are involved. So we've seen that if you take 2 samples of water, same amounts of water, 100 mils of cool water, 100 mils of warmer water, their temperature settles in the middle, right? So we've got 100 mils and 100 mils, and we've got 18 degrees C, and we've got 22 degrees C. They're going to settle right in the middle at 20 degrees C. But others of you did other things. So we've got some people that added different amounts of water. So we have to look at that. So kind of the thought experiment to do there is, okay, if you had 100 mils of water at 18 degrees C, and instead of doing this scenario, if you decided to add 200 mils of water at 22 degrees C, what do you think they would settle on for a final temperature? So you want to kind of think about that. Now, we're going to get better mathematically at predicting that, so you're not just kind of guessing, but just even without having the formula at hand or trying to do the math, just kind of go through mentally and think, all right, how would that be different? If I'm no longer doing 100 mils of this and 100 mils of this, now I'm doing 100 mils of this and twice as much of this at 22 degrees C, what do I think that's going to do in terms of where my final temperature settles? Because here they settled right between the two. Right between 18 and 22 is 20. So they both settled at the same final temperature, and it was dead smack in the middle. So now we're asking, okay, 18 and 22, what's going to be the final temperature here? Is it still going to be 20, or is it going to be something else? Is it going to be closer to 18, or is it going to be closer to 22? And what we want to think about is why that happens. So you want to kind of have some thoughts in your head. You're doing some reading as part of that lab report too that's going to help you put some numbers on this. But what we're trying to figure out is how does that final temperature get impacted by what you're combining, right? So then we've got, let's clear some of this out. So another thing to think about, so those are some water examples. You can add different amounts of water at different temperatures and maybe get a different result, and we should think about why that is. But some of you guys took, some water. So for example, there was water at 40 degrees C, and then a piece of copper, so one of those little copper cylinders. So this was 66.51 grams of copper at 53.75 degrees Celsius, and we put that in there, and that seemed to work. So the final temperature, so again, hot metal goes into cooler water. We know the water's going to heat up some, the metal's going to cool off some, and they're going to settle at the same final temperature. And it turns out this particular combination worked pretty well. So the final temperature was 42.1 degrees Celsius, I think. So when we look at the temperature change for our water, the water went from 40 degrees Celsius up to 42.1. So that means our temp change was 2.1 degrees Celsius. So that's pretty close to our target up here, which was 2 degrees Celsius. So there's other ways to do it. You can pour warmer water into your water in your styrofoam cup, or you can take a piece of hot metal or warm metal and put it in there. So whatever you're doing, your goal is you're providing that heat energy. You're providing that Q into the water, and you're bringing its temperature up. You're getting those molecules moving. So, and then what we got to think about here is, all right, so that worked. So that was adding copper to the water. Now here's an interesting thing. Let's say, so I'm just going to change the color here so we can see what's going on. So same scenario, 40 degrees Celsius water, but in this case, let's say I'm adding aluminum. Okay, so I'm going to add an aluminum cylinder of the same mass. Okay, so a 66.51 gram cylinder of aluminum. Now, one thing to consider is that mass of aluminum looks really different, right? So copper, pretty small cylinder, weighs 66.51 grams. This is aluminum, and this is 66.51 grams, and it's a much bigger volume. Go away. So that's one thing that we have to think about. So there is a difference here. But in both cases, I'm going to add 66.51 grams of metal. But in the case of the aluminum is going to go in at 47 degrees Celsius. All right. So if I dunk that into my 40 degrees Celsius water, it turns out I still get, so here's my 47, here's my 40. The final temperature, I think on that one was like 40.2 degrees Celsius. So still pretty close, change in temp of 2.2 degrees Celsius. But look at how it had to be gone about, the differences. So in both cases, I'm starting with water at 40 degrees Celsius. I'm trying to bring that water's temperature up to 42 degrees Celsius. I can accomplish that by adding this mass of copper, 66.51 grams of copper, at 53.75 degrees Celsius, okay? So it has to be that warm in order to accomplish this temperature change, okay? So the temperature change I'm trying to get to, I have to heat the copper up to a temperature of 53.75. Now, I can use aluminum, too. I can pick a different metal, heat it up, and then I can dunk it in the water, and I can accomplish the same goal, right? I can bring the temperature up to 42, temperature final, no, that should be 42.2, sorry guys, 42.2. So I can bring the temperature up by adding aluminum instead. But some things are going to change. So even if I add the same mass of aluminum, I'm not necessarily going to get the same result. So if I want to add the same mass of aluminum, then that aluminum needs to be at 47 degrees Celsius to affect the temperature change. So that aluminum's going to cool down, the water's going to warm up, they're going to settle at the same final temperature. That's that key point of when you put two things together, they're going to settle at the same, final temperature point. We got to think about what that looks like on the molecular level, on the particle level. But that's kind of what we're playing around with. So if I clear this stuff away. So what I want you guys to be thinking about, and you've probably, if you've been doing the reading that was assigned on this is probably the most inefficient way of erasing something. This is just like when I'm in class and I'm using my hand on the whiteboard. I just can't get away from this situation. So some things that you want to consider are, what were all the factors? So I'm trying to add a certain amount of Q, right? So I'm trying to add a certain amount of energy in order to accomplish this change in temperature. And what I need to think about are all the factors that are involved. So one thing that I have to look at is we've been looking at volume or mass of the water that you're trying to heat up. So some of you guys used a lot of water and you were trying to heat up a lot of water. Some of you were using very small amounts of water. So volume or mass of water. So that seems to matter. So kind of the question is, do we care about mass? Oh my God, Sarah. Jeez. Do we care about mass or do we care about volume of the water? Or maybe both. And then the substance that you put in, that seems to matter too, because aluminum behaves differently than copper. So there must be something about the nature of what you add that can change things. So what's the substance that you add? And then how much of the substance do you add? So in the case of the hand warmers, the iron and stuff like that was added. So there was an experiment run with that where adding, I think, 7 grams of that didn't quite accomplish the goal, but adding 10 grams of it did accomplish the goal. So there's something about how much of the stuff you add. There may be something about how much water did you start with that determines how much Q, how much energy you need to add to get this to happen. And something about the nature of the substance that you add. So it matters whether you're adding warm water or warm copper or warm aluminum or the substance inside a hand warmer. So you're going to encounter an equation for all of this. And it's probably going to look something like Q equals MC change in T. And that's going to be something where, can you survive by just memorizing that formula and plugging numbers into it like it's some algebra problem that you don't give a shit about? Yes, you can. If we can get to the point, though, where we understand why that's put together the way it is, we're going to be a lot better off. So now we know that Q is how much energy is involved in this process, and you can either add energy or you can take energy away. So we're going to play around with Q, being how much energy are you providing or taking away from your system. We're going to be looking at mass. We seem to have an indication that mass has something to do with this. This change in temperature, this is our goal, right? So this is the goal we're trying to accomplish. We're trying to change the temperature of the system. This is the energy we're going to put into it to accomplish that goal. And then we got this mass thing, and we're like, is that the mass of the water? Is it the mass of the aluminum? Is it the mass of the copper? Is it the mass of the hand warmers? Like, we don't necessarily know. But this little guy in here, this is something that we're going to talk about together in class. This is what's called specific heat. And it has a very specific meaning. But for now, we're going to use this specific heat term to kind of represent the differences in substances. Because what you guys saw was that even when you added the same mass of aluminum or copper, they behave differently. You have to heat them to different temperatures. They have different effects on the water. So there's something about aluminum that's different from copper that has something to do with how it heats water. So we have to care about what substance we're putting in, right? So what is it? Water? Is it aluminum? Is it copper? This specific heat term that we haven't talked about a whole lot yet, but hopefully you've been doing some reading about it, that's what's going to help us figure out, like, what is it about aluminum that behaves differently when you're trying to heat up water? What is it about copper that behaves differently? What is it about water that behaves differently? So now we've at least got a handle on what these terms are. It's going to be a lot of practice with this, but as much as possible, I'm going to try and have us focus on the concepts behind it. Because if you just become a calculator, just grabbing numbers and plugging them into that, that's not going to serve you. There's no point to that. I mean, it's important to be able to use formulas, but it's not going to add to your mental model of how the world works. So that'll be our next goal, and that'll be what we work on in class together.